In the last video we were looking at this particular function. Now we said that the domain x could not equal 1, but in this video we are going to allow 1 to be the domain of this function. So here's the graph that we saw previously. Now notice something about this graph. Notice that the curve appears to be approaching this dotted red line as x gets larger and larger. You can see that the dotted line passes through 1 on the y-axis. So the value of the function appears to be approaching plus 1 as x gets larger and larger. As a matter of fact, the function is approaching 1 as x gets larger and larger. So we say that the limit as x tends towards infinity, well, to be more accurate I should say positive infinity, of f of x is 1. So it means that f of x can be made as close as we like to 1 by making x sufficiently large. Now it turns out that if we make x sufficiently large but negative, in other words if we keep going off towards negative infinity, then our function is also approaching 1. So we could indicate that by writing the limit as x tends towards minus infinity of f of x is 1, means that f of x can be made as close as we like to 1 by making x sufficiently large and negative. So we're dealing with large negative values. I could say they're small values, but small sounds like we're talking about values that are close to naught, and obviously that's not the situation here. We're dealing with large negative values of x. Now how can we see that without drawing a graph? Well, we could write our function like this. We could divide above and below by x. By the way, x cannot equal 0, because then we would be dividing above and below by 0. We'd have 0 over 0, which is indeterminate, as we saw in the previous video. But that's okay, because x is going to be nowhere near 0. We are going to be letting x go towards plus infinity or minus infinity. So we don't have to worry about x being equal to 0. So if we divide above by x, well, we get x divided by x is 1. Then we have plus 2 divided by x. And underneath we have x divided by x, which is 1, and then we have 3 divided by x. Now, with our function in this form, let's take the limit as x tends towards infinity. Well, let's suppose that we take plus infinity first, although you'll see that it won't actually matter. Well, what's going to happen? Well, as x goes off to infinity, what's going to happen to 2 divided by x? Well, we know that if the denominator of a fraction gets bigger and bigger, then the entire fraction is going to get smaller. It's going to go towards 0. We can make 2 over x as close as we like to 0 by making x sufficiently large. And similarly for 3 over x, we can make 3 over x as close as we like to 0 by making x sufficiently large. So f of x can be made as close as we like to 1 by making x sufficiently large. So the limit as x tends towards plus infinity of f of x is indeed plus 1. Now let's just get a better feel of what's going on here. Well, we know the limit that f of x is approaching 1 as x gets larger and larger and positive. Let's just take a very large positive value like plus 1 million. Let's plug plus a million in for x. Well, we've 1 plus 2 over a million, that's 1.000002, divided by 1 plus 3 over a million, that's 1.000003. So we get a positive answer. And notice also that this number on top is smaller than the number underneath. So that means that this fraction is less than 1. So as x tends towards plus infinity, f of x is indeed approaching 1, but it's approaching it from below. And that's exactly what we see here in the picture, in the graph. See, for values of x that are greater than 0, f of x is less than 1, but f of x is approaching 1 as x gets larger and larger. Now for large negative values of x, we see that f of x is also approaching 1. See, as x heads towards minus infinity, obviously 2 over x is still going to go to 0. But of course 2 over x will be negative in this situation. For a very large negative value of x, 2 divided by x will be negative, and 3 divided by x will be negative. But as x gets larger and larger and negative, both of these will go to 0, so the limit will be 1 also. Let's take a very large negative value. Let's take minus a million. Well, we plug minus a million in for x to find f of minus a million, so we get 1 plus 2 over minus a million. That's 1 minus 2 millionths, or 1 minus 0.000001, or 002 I should say. That's 0.999998. If we plug minus a million in here, we've 1 minus 3 millionths. That's 1 minus 0.000001, or 0.999997. Notice that the numerator on top is greater than the denominator. So that means that this fraction here is greater than 1. But it's very close to 1. So if we look at the graph of f of x is greater than 1 for large negative values of x. We're not going to worry about what happens around minus 3. We'll cover that later on. But for large negative x, the value of the function is greater than 1, but it's approaching 1. Let's take a different function and consider the limit of it at infinity. Well, actually it doesn't matter whether we've plus or minus infinity here, we'll get the same answer. So you could experiment with plugging very large numbers in for x. Say plug 1 million in for x and see what kind of a value you get. Then plug in 1 billion and see if the values for the function are approaching some limit. That's one way you could do this. But the usual way is to divide above and below by the highest power of x. And that's an allowable operation because x is not 0. We're not dividing by 0. X is going to be a long way from 0 when we take the limit as x tends towards infinity. So that's an allowable operation. So if we divide the top by x squared, 3x squared divided by x squared is 3. Minus 7x divided by x squared is minus 7 over x. And then we have 4 divided by x squared. And in the denominator we have 5x squared over x squared, that's 5. 2x over x squared is 2 over x. Minus 10 over x squared. So we know that as x tends towards infinity, and it actually doesn't matter whether it's positive or negative infinity, these 4 fractions will go to 0. Okay, the denominators will blow up, and when the denominator of a fraction blows up, the entire fraction approaches 0. So you will find that the entire function is approaching 3 over 5. So we can make f of x as close as we like to 3/5 by making x sufficiently large, either a sufficiently large positive number or a sufficiently large negative number. So we could be taking the limit as x tends towards plus or minus infinity here. So that was limits at infinity. Now I just want to go back and explain what happens near x equals 3 for this function. So we're no longer dealing with limits at infinity, but for this example here we're taking the limit as x approaches 3 of our function. Now you can see from the graph this should actually be minus 3. You can see from the graph that as x approaches minus 3 from the left, the function appears to be blowing up towards positive infinity, and as x approaches minus 3 from the right, the function seems to be blowing up towards negative infinity. So for one thing, the limit at x equals minus 3 doesn't exist because we're getting different results depending on whether we are approaching x from approaching minus 3 from the left or approaching it from the right. Okay, just to see what's going on again a little bit more clearly maybe, let's take a value that's close to minus 3 but less than minus 3, like well actually this value is greater than minus 3. if we plug this in, we get minus 2.999 plus 2. Well, that's minus 0.999. And in the denominator we've minus 2.999 plus 3. That's 0.001. So we've minus 0.999 divided by 1000. That's minus 0.99 multiplied by 1000. That's going to be minus 999. So we get a large negative value. So that's for a value of x that's greater than minus 3. We get a large negative value. On the other hand, if we take a value that's less than minus 3, so a value that's to the left of minus 3 but close to minus 3, so here we're taking minus 3.001, plug it in for x here, we get minus 1.001 on top, and we get minus 0.001 underneath. If we work this out, we get plus 1001. So we get a large positive value for values of x that are less than minus 3 but close to minus 3. We're going up to a large positive value. Okay, this line here, this vertical line that acts as a boundary between both parts of the graph of the function, is called an asymptote. Since it's a vertical line, it's called a vertical asymptote. Its equation is x equals minus 3. Now we saw when we were taking limits at infinity that the function is approaching 1. It's approaching 1 from above as x goes towards minus infinity. It's approaching 1 from below as x tends towards plus infinity. So the horizontal boundary line, if you like, between the two graphs is called a horizontal asymptote. The equation of this asymptote is x equals 1. I'm sorry, this line has equation y equals 1. All the points on this line have a y value of 1.